Good afternoon, everybody. Today, I talk about the development of REE resources of Malaysia and integrated approach. First, there are four main points in Malaysia. Number one, Malaysia is enriched in ion adsorption clay, or what we call IAC, or locally we call non-radioactive rare earth elements deposits. I will elaborate on this later. Number two is very important, that rare earths currently is the hottest commodity in the world because of the new energy initiative and the monopoly of REE supplies by China. Point number three, Malaysia should capitalize on our rich REE deposits to become a major player in the world REE supply scene. And number four, in order to capture the full value chain of REE, Malaysia should focus on the vertical integration of the REE industry by going downstream from the raw mine products. Now, everybody know what are the rare earths. They are in the lanthanide series of the periodic table. But out of their 17 elements of rare earth REE, there are only four, which is praseodymium, neodymium, terbium, and dysprosium, PrNd, TbDy. These four very important elements constitute 92% of the total value chain of rare earths. These elements are used in various applications, including power tools, luminance, lighting, display screens, medical, wind turbine, electric vehicles, cameras, as well as magnets, but also important component in the defense industry. All of these involve various kinds of rare earth elements, but most critically is PrNd, TbDy, and I will explain why. Now, TbDy and NdPr, these are the elements that is critical to make something what we call a supermagnet. And a supermagnet is what we use in the electric cars as well as wind turbine in their motors or in the electric generators. A typical electric car use about 1 to 2 kilograms of NdFeB magnet. Now, NdFeB magnets offer the highest energy product of any permanent magnets material on the market today. They are used in drive motors, in hybrid cars, electric wind turbines, servo motors, electric medical devices, and so on. A typical NdPr magnet will take about 30 to 33% of Nd and Pr. In order to make them into high temperature tolerant, between 3 and 5% of TbDy is added. Now, there are two different types of REE deposits in Malaysia. One is what we call the mineral type, which you must have heard about it. It is like what Lenas is doing. The mineral type of rare earths comes from minerals. They are from monazite, magnesite, and xenotime. Rare earth elements occur as a mixture of various elements attached to the minerals. They are usually very low in the heavy rare earths. And to extract rare earth from them, you have to go for high pressure autoclave, what we call cracking, to release the rare earth into a solution so that it can be separated into the product, like what Lenas is doing. In the process of cracking, you leave behind a residue which is thorium bearing, which is mildly radioactive. Currently, the radioactivity level is around 7 BQ per gram. It is higher than the standard of 1, but it is not fatally dangerous. Number two, the ion adsorption clay type of rare earth is totally different. It is formed by the dissociation of the minerals of rare earth, and the rare earth ions got attached to the clay in the residual soil. So the way we do it is to leach out the rare earth elements from the soil, and then we precipitate them into a carbonate called MREC, mixed rare earth carbonate. These are usually not radioactive because even if there is any thorium value in the soil, they are not leachable by the solution. That's why the cake usually has about 0.1 BQ per gram, much lower than the 1 BQ radioactivity level. That's why we Malaysia call this deposit non-radioactive rare earth deposits. Now, this is a slide to show you how the REE or IAC deposits are formed. Basically, the rock, which is granite, that contain rare earth elements, has gone through a series of weathering and formed residual soil. In the residual soil, the rare earth element would migrate down with the groundwater, and along the way, they got attached to the lattices of sheet silicates like kaolin. So that's why you can see that if you look at the soil profile, there's usually an enrichment of REE at the middle section of the weathering zone, or what we call horizon B and C. And another telltale sign is that usually cerium elements are enriched in the upper portion of the soil profile. So much so that if we geologists were to look at fraction of any sample that we take, if we find that there is a high cerium content, that means the deposit is shallow, or they have taken a sample from a shallow portion of the deposit. So, back again, the rare earth formation is through the leaching and the absorption of the rare earth onto the clay. So basically, in real life, the IAC deposit is no different like when you spill coffee on your white shirt. So the white shirt is your clay, and the coffee is your ion of rare earth. And of course, you cannot wash coffee out of your white shirt by water. You have to use a special detergent. Similarly, the rare earth element that has been attached to the clays in the soil profile cannot be leached out by water, but you can use a certain chemical which we chemists call lixiviant, which is a solvent such as ammonium sulfate, to dissolve the rare earth to take it out into a solution form. So remember, ion adsorption clay type of mining is not conventional mining. It's actually a leaching, a washing process. You are washing the rare earth element from the clay out. You are not mining the clay at all. In Malaysia, geologists have done work studying the rock or the granite igneous rock of Malaysia and found that on average, whole country, our rock formation contain about 227 parts per million of total rare earth oxide. Now, weathering of this rare earth oxide would eventually end up into the clay. And if you look at the average thickness of weathering of about 50 meters in Malaysia, you look at the area of exposure of all the granite, you multiply that volume by the density of the rock formation, multiply by 227 ppm, you will know how much of rare earth would have been released through the weathering process, and that could give us a magnitude of guesstimate how much IAC deposit potential there is in Malaysia. Apart from, we still of course need to do drilling and sampling. Now, geological survey as well as earlier work by various researchers has found that the Malaysian, we have at the moment at least 16.2 million tons of ion adsorption clay deposits in our country. Now, this is equivalent to currently about 3.8 trillion ringgit, which is actually equivalent to about 1.5 times the size of our Malaysian oil reserves. So it shows that this industry is significantly very, very big, and therefore the country must pay full attention in its proper development. Our Malaysian IAC deposits contain a high concentration of valuable magnetic metals and HREE fractions. Here I need to explain what is heavy rare earth element or HREE. We divide the elements of rare earth by their atomic numbers. The higher the atomic numbers, we call them the heavy rare earth. And the cutoff line is between gadolinium and terbium. Now, the light rare earth is very plentiful in the mineral type, but heavy rare earth, they are very scarce in the mineral type. They are only enriched through the ion exchange process in the leaching and deposition of IAC deposit. They explain why in the world, heavy rare earth deposit is only formed in the IACs around the tropical region. And Malaysia, we are lucky enough to be endowed with IAC. Our typical Malaysian deposits contain about 4.3% of TBDY, which is very, very critical. So we are very valuable in terms of heavy rare earth deposit. This is a slide to show you how a typical mining of IAC deposit is done. Basically, after you have identified the ore body, which is colored green in this slide, you would drill an injection hole to the top of the ore body, and you slowly drip in lixiviants or solvents into the ore body, and then the lixiviant will percolate through the ore body, and you collect at the gravity low point to recover the solution like this. So the solution will flow out, you collect it, you precipitate out the rare earths, and you recycle the solvent back into the ore body to leach again. Of course, in the process, you need to adjust the chemistry. Now, it appears to be very simple, but to do a proper job, we have to study the hydrology, meteorology, geotechnical study to ensure that the moisture, the extra lixiviant that we inject into the ground do not exceed the liquid limit of the slope, so that you will prevent landslides of geotechnical hazards. As well, we also need to control the groundwater flow to ensure that there's no extra contamination of groundwater, and there are many ways and means of civil engineering or geotechnical methods to control the flow of underground water. For example, a fence of high pressure, hydraulic high fence by using well points to control the flow of it. So it is important, although it appears to be simple, the mining of IAC has to be done properly to ensure minimal damage to the environment. This is an example of a real-life IAC mining. This is from the pilot project in Kenering. If you can notice carefully, you look at that, the injection wells are spaced very closely between 3 and 5 meters between holes, but they are usually very, very shallow. And they are only injected on average about 1 cubic meter per hole per day. So it's a very slow drip into the ground. And you can see that while the work is ongoing, the rubber tapping activity can keep ongoing because you do not damage the tree, you do not cut the tree. The most you do is to clear the path for your pipes. So at the end of your mining operation, after flushing the grounds clear, you remove all these pipes, and the ground, if it's a jungle, it will grow back to itself, the undergrowth. If it's a plantation, the works continue. So actually, this is actually a very pleasant way of mining, whereby very minimal disturbance to the ground is there, and the footprint is actually, disturbed footprint is usually not very big. There is also a research going on as to, apart from using a conventional way of using ponds to precipitate rare earths, we also have a design whereby you're using nanotechnology to shorten the precipitation time of rare earth carbonates by using instrument or equipment called G-Nano REC plant. In the value chain of rare earths, when you do mining, when you put the first product you have is MREC, mixed rare earth carbonate. When you sell that as a raw material to the separation plant, currently in the whole world, wherever there is any project of IAC, the products are all sold to China, because only China currently has the separating plant capability. So the value of the REC that is sold out currently only constitute about 20% of the total value chain of rare earth. Now, if you able to go to separation and produce pure products from the MREC, you are going to get around 50% of the total value. And with the pure product, if you turn it into metal and alloys, you get up to about 65 and then eventually to 95% when you make the magnet and the component products. So it is important for a country like Malaysia that when we do have such substantial resources of IAC, we should try to go up the value chain as much as possible. So this is the evolution of a typical rare earth deposit industry. You start by exploring what is available in the ground. While after you identify the reserves, of course you design your mining operation. Then you produce REC, the rare earth carbonate. You send to a separation plant where the rare earths are separated into their individual oxides. These oxides will then turn into metals, alloys, and magnets and components. And at the end of life usage, the components are recycled and go back to the separating plant to pick up whatever rare earths again. So this is a complete circle of rare earth value chain. We can see very clearly that the square of yellow, I show you that separation is the most critical bridge between upstream mining and downstream manufacturing. So it is important for Malaysia to develop our own separation technology so that we can enhance our value. Currently in the world, there are not many REE separating projects other than China. In the world, the only one that is commercially operational is Lynas, which is in Kuantan, but they are dealing with light rare earth mineral type. There's another smaller one in Estonia doing also mineral type, very small, about 3,000 tons a year. The rest are still in the planning stage. So you can see that the whole world, whenever you produce rare earths, is all flowing into China. The rare earth separation itself is actually not a rocket science. It's a very complex chemical process because between various rare earth elements, the separation factor between them is very, very small. So therefore, you need to dissolve the rare earth and then you mix it with an extractant, usually is in the oil phase. So you mix them very well so that certain elements of a higher atomic number will go to the oil phase and the smaller atomic number rare earth will stay in the aqueous phase. After mixing, you let them settle, so you achieve certain degree of separation between the oil phase and the liquid phase. But because at any particular point, the equilibrium separation is actually very small, so you have to repeat this process both upstream and downstream of it. So that's why that shows the complex flow sheet, as you can see from the bottom section of the diagram. It is a very complex process and very sensitive to parameter changes in chemical parameters. Any change you can affect the whole equilibrium. So sometimes it may take months to stabilize a separation line in order to achieve pure products. And they explain why it is so complex and why is it that not many people is doing rare earth separation. I'm lucky to get involved with a group that has now developed the first rare earth separation plant in Malaysia, and with collaboration with a company from France, Caresta, whose original people were the people who originally designed Lynas separating plant. They're working together in Malaysia now, and they are now capable of doing the full separation of rare earth all the way down to heavy rare earth oxide. So currently, there is a capability of Malaysia having a full rare earth separation in the country, and I believe the first pilot plant could be operational by the end of this year. You can see that projected in the world, there is going to be a supply-demand imbalance because basically dysprosium is a heavy rare earth and they are not commonly found. So a development time takes longer than consumption's development. So you can see that as the years go by, we can see that there's going to be a large gap between supply and demand. So the only way to solve it is to quickly put good deposits into production because these are critical for our global target of net zero. If you want to do new energy initiative, you need dysprosium and rare earth to make supermagnets, to make electric car, and to make wind turbine. Similarly, terbium and dysprosium, you can see that the green line in here is going to be the supply-demand index. And the gray line is what I call it, the price in, projection. It's a bit too long to describe here, but just generally to say that there is going to be a shortage of terbium and dysprosium. Similarly, there is going to be a slightly lesser shortage of NdPr because NdPr is more abundant than TbDy. However, all these four elements are critical for the manufacture of supermagnets. Of course, now with the whole world of awareness of ESG, for Malaysia to develop our own integrated rare earth industry, we have an advantage because we start from day zero. We have a piece of blank paper to design our plant from mining, exploration, mining, separation, manufacturing. So we would advocate that we would follow whatever ESG criteria. So here, the REIA of Europe come up with 16 criteria for us to work out what is the point, put up all the ticks so that ultimately the Malaysian product can have a good product passport showing that we are of high ESG scoring, and that will put us in a high position in international marketing of products. Now, of course, there are issues. These are the same issue that I pick up from Angus worldwide research. But basically, it applied to Malaysia. The main point is high entry bar for new projects because of a high cost, capital cost involved, and the uncertainty of the market price. Of course, there's red tapes that permitting delays. Sometimes it may take up to 2 years. Legislation and what they call the acts going for, is it far enough to protect the industry? Geopolitical tensions, ESG, recycling, magnet production costs, and volatile price environment. All these issues that we need to address, but it is a commercial issue. So we believe by doing all this, Malaysia can achieve a fully integrated REE industry. Thank you very much.